Namaskar, myself Jaimala, Department of Mathematics, Chaudhary Charan Singh University, Meerut. Today in this lecture series on mechanics, I'll discuss about the derivation of Lagrange's equations of motion and Newton's equations of motion with the help of Hamilton's principle. So, before proceeding to find the Lagrange's equations of motion with Hamilton's principle, you know that previously we derived Lagrange's equations of motion from D'Alembert's principle. So, and now we are trying to derive it with the help of Hamilton's principle. Actually, D'Alembert's principle was a differential principle where we considered the instantaneous state of a system, and then we consider the virtual displacement in it, and then with the help of D'Alembert's principle we have derived the Lagrange's equations of motion. So in differential principle, or you can say in this approach, we considered instantaneous state of a system of particles and then considering a virtual displacement. Lagrange's equations of motion were derived. And there is another approach, which is the derivation with the help of integral principle. And in this approach, what we do? We consider the entire motion of the system. Here the instantaneous state of the system, and in integral principle we consider the entire motion of the system of particle. We consider entire motion of the system of particle between a time interval from time say t1 to t2. Then we consider a deviation, then consider a deviation from it, and finally deviation or the virtual variation, आप कुछ भी कह सकते हो, deviation or virtual variation of the motion and derive Lagrange's equations of motion. So this is the basic difference between the two. And you know what do we mean by entire motion of a system of particle? I have told you many times that by entire motion of the system we mean that first of all the entire system, the system of particles may be represented by a point, system point in configuration space, and whatever path is described by it in the time t1 to t2 is the motion of entire motion of the system of particles. So here we are concerned with the configuration space. So how we proceed to find the Lagrange's equation of motion with the help of Hamilton's principle. This integral principle is the Hamilton's principle about which we are talking in this lecture. So first of all, what is the Hamilton's principle? Hamilton's principle says that for a monogenic system, the entire motion of a system of particles from time t1 to t2 is described along a path for which the line integral L dt from t1 to t2, that is an integral based on the difference between the kinetic energy and potential energy. Line integral is least. So in this Hamilton's principle, this is your line integral. Suppose I say that this be A. Then because A is defined in terms of integral and we are talking about its least value, that means we are talking about its stationary value. So naturally we will use the calculus of variation technique. Here A is a functional because it is defined on function. It is a functional and naturally it is the action function. A is a functional defined in terms of integral. So we will use the calculus of variation technique. Now there are 2 or 3 ways to derive Lagrange's equations of motion with the help of Hamilton's principle, in which I am telling you the first approach. The first approach is that because you are dealing with a system of particles, so we will derive Lagrange's Euler-Lagrange equation in terms for the system of particles, right? So we will use the calculus of variation technique for more than one independent variables. First of all, you see that you are having a system of particle. Consider a system of particles, system of n particles, such that it is described with the help of generalized coordinates q, say qj, such that it is described with the help of generalized coordinates qj, and L is a function of qj dot in time. So you see, in integral 1 or in expression 1, whatever is your integrand, this integrand is based on more than one independent variable. Here qj dot means dqj dt. It is the derivative of qj with respect to time. Qj means j goes from 1 to n. So your L is like q1, Q2, Q आप ऐसे n भी लिख सकते हो where n is equal to capital N, then Q1 dot, Q2 dot, Q3 dot and Qn dot and then time. So your integrand L is a function which is a function of more than one independent variable. And what is the more than one dependent variable? Sorry, more than one dependent variable. Here the dependent variables are more than one and independent variable is one, which is time. So in this case, first of all, we will extend our calculus of variation uh, method or the technique for more than one dependent variables. So this is the one way. So what we do in that case, we will consider uh, an integral, or you can say line integral. Consider line integral j, suppose it is j from x1 to x2, जैसे हमने पहले प्रोसेस किया था वैसे ही कर रहे हैं हम, function of y dot in time, sorry, and x, because here the independent variable is x. But at the time of considering this integral or j, we will write yi dot and x dx, where yi dot means dy dx and I is going from 1 to n. Okay. Now what is our target? Our target is to find the path for which j is stationary. यही तो हम करते हैं कैलकुलस वेरिएशन टेक्निक में. Naturally your function f is a well behaved function. Whatever are the conditions which we use in calculus variation technique will be used here. So there will be one actual path and there will be some variable paths for it. जैसे हम हमेशा से लेते आए हैं तो उसी तरीके से हमारे पास एक एक्चुअल पाथ होगा कोई भी और कुछ इसके वेरिएबल पाथ होंगे. यहाँ पर आपका है x1 क्योंकि अभी हम x के रिस्पेक्ट में बात कर रहे हैं और यहाँ पर है x2. If this is the actual path, then this is fx, y is equal to fx, and these all are the neighboring path. This is the neighboring path, this is the neighboring path, and naturally these paths will be described with the help of certain parameter. So we will assume, let yx0 be the actual path. I have written 0 because I am going to define a parameter. Actual path along which the integral j is stationary. Now we define some neighboring paths. Now define the possible paths between A and B, between A and B, like कैसे हम इसको डिफाइन करेंगे. y1, पहले मैं 1 के लिए ले रही हूँ, x अल्फा is y1 x0 plus alpha eta 1 x. Suppose I have defined this path with the help of the parameter alpha and eta 1. Then what is the condition? That eta 1 is 0 at x is equal to x1 and x is equal to x2. Similarly for the second dependent variable, the path corresponding to second dependent variable will be y2 x0 plus alpha eta 2 x, where again eta 2 is 0 at x is equal to x1 and x2. Similarly, you can define the neighboring paths corresponding to all the dependent variables yn x0 alpha eta n x. So these are the paths which we will define for which are representing the neighboring paths corresponding to the different dependent variables. These eta 1, eta 2 to eta n are well behaved functions. These are auxiliary functions, and naturally these are the functions of the type which are required for the calculus of variation technique, to use the fundamental lemma of calculus of variation technique. Now naturally your j corresponding to 4, your j will be a function of alpha. Corresponding to 4, j will be represented as, you can write it as j alpha. It is x1 to x2. I have written in it as function of yi depending upon x alpha, yi dot again depending on x alpha, and x, and this is dx. Okay. So I have to make it stationary, or I have to find the path for which 5 is stationary. As j is a function of alpha, so for stationary value of j alpha, I'll put delta j to be 0. It is the virtual variation in j. Now what is this delta j? This will be delta j delta alpha because now j is a function of alpha. So I'll calculate it, this delta j delta alpha. Now delta j delta alpha will be, or initially I may write only delta j delta alpha. This will be delta alpha x1 to x2 function of, I am just writing yi dot and x dx. But you know that alpha is not varying corresponding to x coordinate. This is varying with respect to the y coordinate. I mean, this has variations corresponding to x in terms of y. So this alpha may be entered x1 to x2 delta alpha. Naturally it will not operate on dx because then its value will be 0. So I'll operate it only on f, yi dot x dx, right? Now open it, you will get delta f delta yi delta alpha, because f is a function of yi, plus delta f delta yi dot delta alpha. And if I take the variation of f with respect to x and then variation of x with respect to alpha, naturally it will be 0. So I am not writing it here, I am just writing up to this. Okay. This 4 may be written in short as yi x alpha. सबको मिला के हम ऐसे लिख सकते हैं, is yi x0 plus alpha eta I x. ऐसे इसको लिखा जा सकता है, where what is I? I is going from 1 to n. So if I break it into two parts and calculate it in the same way as I calculated in the calculus of variation technique for a single variable, I'll get the same type of equation. First of all, I'll write delta J delta alpha. It will be delta F delta yi plus delta F delta yi dot delta yi dot, because delta y delta alpha will be delta y, and delta y dot delta alpha this delta y will be delta y dot. तो ये मैंने यूज करके यहाँ पर इसको चेंज करके लिख दिया है, delta y dot delta alpha. Now again, by breaking it into two parts, I may write delta J is equal to, there it was delta F delta yi plus delta F delta yi dot delta yi dot, and this was dx, and initially it is from x1 to x2, which I am not writing again and again, it is understood. Now break it into two parts, delta F delta yi dx, and for this part I'll write delta F delta yi dot, and this delta yi dot may be written as derivative of delta yi, right? So we will use it. It is not a derivative with respect to time, it is a derivative with respect to x. With respect to x, delta yi dx. So we'll integrate it by part. It will be first function, then integral of second function, which is delta yi for x1 to x2 minus derivative of first function, and then integral of the second function, which is delta yi dx. Now what is delta yi at x1 and x2? It is 0. Delta yi at x1 and x2 is 0, because at the end points there is no variation in y. All the curves are meeting at the same point. Both the terminal points are same for all the curves, so it will be 0. And finally delta j is equal to x1 to x2 delta f delta yi, and this one minus derivative of delta f delta yi dot delta yi dx. This is delta j. Now for stationary value of j, delta j is equal to 0. So this implies for this integral, suppose I am giving it the number a, then because delta yi, it is true for all delta yi, it is true for all virtual displacements of y. So it is true, it will be true only when this integral is 0, integrand is 0. Secondly, delta yi may be represented in terms of eta function, and eta is a well behaved function. So by fundamental lemma of calculus of variation, the integrand should be 0. Now A implies delta f delta yi minus ddx of delta f delta yi dot is 0. Now what is the Hamilton's, what was in the Hamilton's principle? If you compare it, if you compare your J with the Hamilton's principle, so what will happen? Compare J with इसको लिख लेते हैं, J क्या था? Compare J is equal to x1 to x2 function of yi dot and time, sorry, and x, yi dot and x dx with Hamilton's line integral. This is t1 to t2 L of qi dot and time. What will happen? मैं सोच रही हूँ इसका इक्वेशन नंबर 6 था, तो ये हो गया 7 और 8. This is 7 and this is 8. Comparing. What is yi? Y is I may be replaced by qi. Yi dot will be replaced by qi dot. X will be replaced by time. X1 with t1 and x2 with t2. And f is replaced by L in 8. ये कंपैरिजन से हमें पता चला. तो क्या आया? Then 8 implies delta. What is f? F is L. What is yi? It is qi minus d dx. Here it is d dt because x is replaced by t. Then delta L delta qi dot is equal to 0. So what is it? It is Lagrange's equation of motion. Euler-Lagrange equation of motion. 9 is Euler-Lagrange equations of motion. So we have derived Euler-Lagrange equation of motion with the help of Hamilton's principle. There may be another approach to find its derivation, like you may also proceed by taking L, like your integral was, suppose I am saying it is to be A. A was, this is the second way. You consider A, your A line integral is T1 to T2 L dt. Okay, you write it as T1 to T2 L. L is a function of qi dot and time, and then you find what is delta A. Delta is delta of T1 to T2 L qi dot and time, integral with respect to time. Enter this delta inside, operate on L qi dot and time. You again will define the paths and then write it as T1 to T2 delta L delta qi delta qi delta L delta qi dot dt. Now again adopt the same process as we adopted in the first method, and you will get finally the Lagrange equation of motion. So you can also proceed by considering this much. So this is all about derivation of Euler-Lagrange equation of motion by Hamilton's principle. Similarly, sometimes it is asked that derive or deduct the Hamilton's principle. So how will you deduct it? You say that in Hamilton's principle, the line integral, which I have written here, A, should be stationary. This is the Hamilton's principle. Stationary along the actual path. Right? So you can say that consider T1 to T2 L dt and write this L as T minus V dt. Now apply the delta or variation L dt. You will get T1 to T2 delta of T minus V. Again solve it with the same approach, and solving you will get this equation of motion. You will get solve and get delta L delta Qi this will be minus, अच्छा बाद में आएगा वो, आप इसको सॉल्व करेंगे एंड यू विल गेट डेल्टा एल डेल्टा क्यू आई माइनस डी डी टी ऑफ डेल्टा एल डेल्टा क्यू आई डॉट is equal to 0. So you will say this is the Euler-Lagrange equation which on solving provides the actual path. So this actual path is obtained by putting the variation of this line integral to be 0. It simply means that the line integral, this one, is stationary along the actual path. So this is all about the deduction of Hamilton's principle. Hamilton's principle के डिडक्शन में आपको ज्यादा कुछ नहीं करना. आपने एक लाइन इंटीग्रल माना, ये लाइन इंटीग्रल आपने एज्यूम किया, राइट. एज्यूम करने के बाद आपने इसको t माइनस वी के फॉर्म में लिखा, उसी तरह से डेल्टा वेरिएशन लिया, सब कर आके जब आप इसका कैलकुलेशन करेंगे पहले की तरह से, तो आपके पास ये इक्वेशन आ गई. अब हमें पता है कि ये जो इक्वेशन आई है ये आयलर-लैग्रांज इक्वेशन है. आयलर-लैग्रांज इक्वेशन वो इक्वेशन होती है जिसको जो भी कर्व पाथ सेटिस्फाई कर दे वही एक्चुअल पाथ होता है. तो हमने कहा कि ये हमें मिला इसको इसकी स्टेशनरी वैल्यू से. तो बेसिकली रिवर्स वे में अगर चलें तो हम ये कहेंगे कि दिस इज द इक्वेशन which is Euler-Lagrange equation providing the actual path, and this actual path is obtained by putting the variation of this line integral to be 0. And where we put the variation of this line integral to be 0, we put it in Hamilton's principle. So this is the deduction of Hamilton's principle. So this is about derivation of Lagrange equation with the help of Hamilton's principle by the two approaches, and this is the deduction of Hamilton's principle. Similarly, this is very simple to deduce the Newton's second law of motion with the help of Hamilton's principle. कैसे करेंगे हम उसको? अगर हमें न्यूटन्स इक्वेशन ऑफ मोशन को डेराइव करना है, जो सेकेंड इक्वेशन ऑफ मोशन है, with the help of Hamilton's principle. तो पहले तो हैमिल्टन्स प्रिंसिपल लिख देंगे हम, जो हम पहले लिख चुके हैं कि वो हैमिल्टन्स प्रिंसिपल क्या कहता है. एंड देन वी राइट दैट अकॉर्डिंग टू हैमिल्टन्स प्रिंसिपल डेल्टा एल डी टी from T1 to T2 should be 0 along the actual path. ठीक है. अब ये L क्या है? This L is T minus V. Again it is T1 to T2. डेल्टा को एंटर कराएंगे हम तो खाली इसी के ऊपर ऑपरेट करेगा, क्योंकि वेरिएशन ऑफ dt विद रिस्पेक्ट टू दिस वर्चुअल डेल्टा इज 0. So it will be delta t minus delta v. Now what is t? T is half m, I write it v square or r dot square. ठीक है. ऑपरेट डेल्टा, डेल्टा टी इज हाफ m ट्वाइस r डॉट डेल्टा r डॉट. ऐसे हो जाएगा ये. तो m r डॉट डेल्टा आर डॉट, ये इसकी वैल्यू होगी। ऐसे ही यदि मैं डेल्टा वी की बात करूं, अगर मैं डेल्टा वी लूं, तो ये आप हैमिल्टन्स प्रिंसिपल से कर रहे हो, हैमिल्टन्स प्रिंसिपल से कर रहे हो तो फोर्स आर डेराइवेबल। तो ड्यू टू द कंडीशन ऑफ हैमिल्टन्स प्रिंसिपल, forces are derivable. For forces F, there exists force potential function. हम इसको दूसरी तरह से लिखते हैं, हम ये लिखते हैं ड्यू टू हैमिल्टन्स प्रिंसिपल, V is a force potential function corresponding to force F. Say it is the force F. Then F क्या है? F is equal to minus delta V. And what is F dot delta R? It is minus delta V dot delta R. And the combination of two may be written as minus delta V. तो ये जो डेल्टा V है, इसकी जगह हमारे पास क्या आ गया? F dot delta R. Now putting these values in 1, 2 और 3 को हम रख दें इसमें, तो 1 implies T1 to T2, डेल्टा T आ रहा है हमारे पास M R डॉट डेल्टा R डॉट dt, और माइनस डेल्टा V आ रहा है प्लस T1 to T2 F डेल्टा R dt इज इक्वल टू 0। थोड़ा सा और इसको सॉल्व कर लेते हैं। इसको हम लिख सकते हैं T1 to T2 M R डॉट, और इसे मैंने लिखा d dt ऑफ डेल्टा R dt प्लस T1 to T2 F dot, F is a force, so it will be F dot delta R dt is 0. Now integrated by parts and then combined it with this second term, you will get T1 to T2 M R double dot minus F डेल्टा R dt is 0. आप इसको बहुत आसानी से सॉल्व कर सकते हो, इसमें ऐसा कुछ भी नहीं है। Now delta R is arbitrary virtual displacement, and therefore this integral will be 0 if this integrand is 0. So from here you got M R double dot minus F is 0, or F is equal to M R double dot. What is it? This is Newton's second law of motion. So finally, with the help of Hamilton's principle, you can derive Euler-Lagrange equation of motion, and you can derive Newton's second law of motion. So this is all about this lecture. Thank you so much.